All right, we'll start. We'll do question two, three, four, and six as our first video, right? Question two was kind of the material I was just talking about in terms of those transitions available and what those mean. So we're looking for an absorption. An absorption means we're going to be going up in energy. So for example, I can eliminate choice D and choice E because we're going down in energy. That would be an emission. We're giving off energy as we relax back down. And then this is a staircase in energy, but remember the first step is the biggest in energy because this is not a linear, right? N equals 1 to n equals 2 is the biggest change in energy because we're pulling a negatively charged electron away from a positively charged nucleus. So each successive step gets smaller and smaller in energy. Um, so I would say, right, n equals 1 to n equals 3 would be the biggest change in energy because n equals 5 is here, n equals 6 is going to be really close together. Those are all really small changes in energy. But the biggest one, n equals 1 to 2, is the biggest change in energy. So most likely n equals 1 to 3 is going to be a lot more energy than 4 to 6 or 3 to 6 for that matter. And we're looking for an absorption, so we want to be going up in energy for question two. All right, that was that diagram that I kind of drew as an example of that staircase and energy. You could calculate it if you weren't sure. We could certainly calculate which one had a greater change in energy. All right, question three, a commonly used laser pointer has a frequency of 5.64 times 10 to the 14 seconds. What is the energy in joules for one photon of this? So we have to know the equations, right? There's only a handful. I give them to you, but we need to know like when do I need to use what equation. So here we've got frequency and we're looking for energy, right? So immediately we should know energy equals Planck's constant times my frequency. So energy equals Planck's constant 6.626 times 10 to the minus 34 joules times seconds times my frequency. My frequency is in inverse seconds, so I don't have to do a unit conversion um, there. So 5.64 times 10 to the 14 inverse seconds. We multiply and seconds cancel out, which is good because we're looking for an energy. We're looking for joules. And somewhere here, I've got my calculator, hopefully. All right, 6.626 times 10 to the minus 34. Multiply that by 5.64 times 10 to the positive 14. And I get an energy, I would say three significant figures. So 3.74 times 10 to the minus 19 joules should be my energy there for question three. Right, to answer the question about question two there, right, absorbed, if energy is absorbed, we're going up. It's like we're gaining energy, we're gaining elevation, right? If we went up the staircase. If energy is emitted, we're going down in energy. That electron would fall down to a lower energy level. It would release energy on the way down. Because remember, what's down here is a positively charged nucleus. So that electron is attracted to the nucleus. It wants to go down, it wants to get closer to the nucleus. It takes energy, it requires energy to pull that electron farther away. That's absorption, right? Emission on the way back down, it brings it closer to the nucleus. And yeah, Cheyenne, 100%, we're not going to see anything in the F block. Like, don't worry about the F block. Um, just because of There's a handful of exceptions in the d orbitals. There's even more exceptions in the f orbitals because of how close they are in energy to the d orbitals. So don't worry about that. All right, question four, right? Rank these forms of electromagnetic radiation from lowest to highest frequency. Another way of thinking about this is the lowest frequency has the lowest energy. So the highest frequency would be also the highest energy, right? We know gamma rays are the highest um, energy. So I'm going to look over here for gamma rays somewhere. Radio waves, they're low. Infrared is in the middle somewhere, right? So now we go back over here. I can cancel that out. I can cancel that out. So yeah, radio waves come first. Microwaves are next. Infrared is next because infrared is right next to visible. So visible would be right here between infrared and ultraviolet. Um, and then ultraviolet, right? That's UV. That is after the visible region. And then what's last would be gamma. Um, X-rays would be between UV and gamma, but that wasn't listed here. So yeah, if you know the general trend, especially within the visible spectrum, so within the visible spectrum, right? Hopefully you know that red light, longer wavelength, lower energy. On the other side, blue, right? Blue is a shorter wavelength, higher frequency, higher energy. Because right after blue is the UV. Um, all right, question six. All right, the lowest orbital energy is reached when the number of electrons with the same spin is maximized. Um, not the greatest like worded question, but we can cancel out a few of these right away, right? Planck's constant is a constant, had nothing to do with electron assignments or configurations. Heisenberg's uncertainty principle just told us basically when and where we could find an electron and basically say we can't exactly say the position and momentum of an electron at any point in time. So we're just left with these three right here, right? Pauli's exclusion principle had to do with we can't have two electrons that have the exact same quantum numbers. So Pauli's exclusion principle, if we looked at lithium, for example, and lithium is 1s2, 2s1, right? Up, down, and up. Pauli's exclusion principle, a violation of that would say, oh, I've got one electron up, the other electron is up. No, I can't have two electrons have the exact same, all four of the quantum numbers. We can't have the same orbital and same spin. Um, the Aufbau principle, we can't really see it with um, lithium, but we can see it with carbon, right? And then Hund's rule. So the Aufbau principle, we want to fill the orbitals from lowest to highest energy. 1s2, 2s2, 2p2. I guess we don't really need to go through this, but right, lowest to highest energy. I guess we could have seen it with lithium. So if this is my ground state configuration for an example, right, we're going to fill the 1s and then 2s and then 2p. So a violation of this would be if we just skipped one of those. Um, and let's say for whatever reason, I took one of these electrons and I kicked it up to a higher level. So um, this would be like a violation of the Aufbau principle, like 1s2, 2s2, 2p1, 3s1, right? That electron shouldn't be here. We skipped a whole bunch of orbitals. So this would be in violation of the Aufbau principle. This question is looking for the Hund's rule. This is saying for our electron configurations, right? Nitrogen 1s2, 2s2, 2p3. If we look at the orbital diagram for that, right? 1, 2, 1, 2, and then 1, 2, 3. We want to make sure each orbital has one electron before we go and pair up electrons. If you notice, this maximizes the number of electrons with the same spin because I put one electron in each orbital before we before we force those electrons to pair up. All right, that was question 2, 3, 4, and 6. Not too bad, 10 minutes in time there. Any questions on those before I start the next segment?